Hello again guys, and welcome back to the first lesson of our first module, Basics of EMI. Of course, in this lesson, we're going to be looking at the why. Basically, what is EMI and why does it matter and why do we care? Also, we'll be looking at some real-world examples of EMI. So let's get started. So what is EMI and why does it matter? Well, first of all, what is the definition of EMI? EMI, which stands for electromagnetic interference, is a major part of the EMC family. The EMC family is electromagnetic compatibility, which also includes ESD, for example, or electrostatic discharge, and others. EMI is unwanted electromagnetic energy that couples from nearby sources into electronics, either by radiation or by conduction, and causes damage or degraded performance. So why do we really care about EMI? Well, first of all, it's for safety and for user experience. And we'll see what that means in real life in later slides. But for now, let's just say that there are standards that govern EMI, and those standards basically say how much EMI your electronic equipment is basically allowed to emit to nearby sources or back onto the grid. Some of these standards are CISPR, FCC, or ISO. So since we've already started talking about EMI coupling, let's cover some coupling taxonomy. That way we're on the same page later on when we talk about coupling. So what are the different patterns of coupling that we have? We have inductive and we have capacitive coupling. Inductive coupling is nothing but magnetic field coupling that happens between different current loops, or between, for example, a transformer to nearby electronics. And basically, the induced voltage due to that coupling is proportional to the mutual inductance multiplied by the IDT. In other words, the bigger the loop area, the more pickup there is. That affects low impedance loops the most. Capacitive coupling, or electric field coupling, is coupling that happens between two adjacent conductors or between a conductor and a plane via parasitic capacitance that exists between those two wires or between the wire and the plane, or between two planes. Okay? The coupled current is proportional to the capacitance multiplied by dV dt. So how fast the voltage is changing on that line or on that node with respect to the other line will affect how much coupling there is. This hits high impedance nodes the most. Then we also have far field plane wave coupling, which is also known as radiated coupling. Radiated coupling is electromagnetic energy or waves traveling between two sources, okay, and turning one of the sources into an antenna that carries that unwanted energy. Conducted coupling is unwanted electromagnetic energy that travels between two components or two electronics or two systems through physical means like wires. Okay? So what are some of the EMI coupling mitigation techniques? So now again, since we're talking about couplings, let's talk about some of the coupling mitigation techniques. Of course, later on in the course, we're going to cover how to take care of coupling on a PCB. For example, sometimes you'd need to rotate a certain component, like a magnetic component, to take care of magnetic coupling. All right, but that's something that we'll get to in later modules. For now, we're going to cover how to take care of coupling outside of a certain module. One of the methods that we use for taking care of inductive coupling is by shrinking loops or by using twisted cables. Okay, when it comes to capacitive coupling, one of the most common ways is by using shielded cables or by grounding cables on one end, not on both ends, because you don't want to create a ground loop. Now, as for the module itself, it is a good practice to be wary of the enclosure integrity such that you don't allow any radiated noise to leave the module or to enter the module. So what are some EMI mitigation techniques? Ideally, we'd like to control EMI at the source. That is by controlling dV dt and the IDT, which, as we just learned, are the main sources of EMI. Unfortunately, though, that usually comes with a price, usually a performance price. So we can't always do that. Alternatively, we could do path control, which is designing the layout for EMI or EMC, or providing shielding, which would protect from radiated emissions. Ultimately, though, filtering is going to be the way to go because it's going to be the most effective method for eliminating EMI. So what are the major differences between radiated and conducted EMI? Radiated EMI is energy traveling as electromagnetic waves, and is mostly dominant above 10 MHz. Conducted EMI, on the other hand, travels through physical means like wires, but it's mostly dominant at lower frequencies. I'm talking like 100 kHz and above. What are some common sources of EMI? Switching power supplies is going to be the number one, of course. Fast edges, high DIDT, high DVDT. DC motors and drives, large DVDT into parasitic capacitance. Fluorescent LED lighting, ballasts, drivers. We'll talk about that in a minute. And then microprocessor clocks and fast I/O. Alright, so what are some real-world examples of EMI? You might have noticed, especially back in the day when we used to have 2G phones, especially if you were in your car and you would get a call, sometimes you would hear some buzzing noise coming out of the speakers. That's actually EMI. Another scenario is in your house, if you have a fluorescent light in a certain room, and in that room you have some audio equipment, perhaps a stereo with some cabling running around, and if you were to turn that fluorescent light on, sometimes you would also get some buzzing noise to come out of the speakers if you have that stereo system on. That's actually EMI. What's going on there is that basically the ballast inside of those fluorescent lights, because they work with a very high frequency, they radiate noise that actually couples to the wiring that you have for your audio system, causing unintended noise to be generated and heard from the speakers. Another scenario is if you're somebody who works with electronics, which I would assume you are since you're taking this course. Sometimes if you are, testing a certain electronic equipment, if you were to apply a high current load on that equipment, sometimes you would get intermittent resets on the MCU, and you wouldn't know why. And that's actually caused sometimes by EMI. So when you apply the high current load, you get a high DIDT. That high DIDT causes the VDD or the power supply to the MCU to take a dip, which in turn causes the MCU to reset. In the next lesson, we're going to be talking about EMI standards and regulations, so stay tuned.